Alright, hello everyone. This is a review, or rather I should say this is a practice final exam for Math 1060. Questions 1 and 2 are from our first learning target evaluating, or from our first standard evaluating a trigonometric function. There were quite a few different types of evaluating, and you can see from where are we here? Right here. Evaluating trigonometric expressions. There were quite a few different learning targets there. So just keep that in mind. Again, with this practice final exam, it says that question 1 is an example of standard 1, which means that it couldn't come from any of those learning targets. So go back to your unit overview, look at your homework, look at past tests that had those same learning targets, and see what types of different questions there were for each one of these questions, just to make sure you're fully prepared. For question 1, we need to first know what the trigonometric identities are. So for part A, sine of 2 alpha is equal to 2 sine alpha cosine alpha. So we know that sine alpha is 8/17, and according to right triangle, if we said, for example, that that's angle alpha, then the sine would be opposite over hypotenuse. And to figure out cosine of alpha, we would need that length there because cosine is adjacent over hypotenuse. So I'm going to call this A. So we would do Pythagorean Theorem. So we need a squared plus b squared equals c squared. So a squared plus 64 equals 17 squared, which is 289. And if we subtract 64 from that, we get 225. And then if you square root 225, that's 15. So then we would have a equals 15. Which means cosine of alpha is 15 over 17. However, if we consider this statement here, alpha is between 90 and 180. That means it's in the second quadrant, or quadrant 2. And in quadrant 2, cosine is negative. So cosine alpha is negative 15/17. So now that we have that information, we can replace in this expression here sine alpha with 8/17, and then cosine alpha with negative 15/17. And options here, I'm fine if you want to just turn this into a decimal or leave it as a fraction. It's up to you. So 2 times 8 times 15 is negative 240. And then we already did 17 squared, or 17 times 17, that's 289. So as a decimal, that's 0.83, negative 0.83. Now for part B, we're going to want to know cosine of alpha over 2, what the identity is for that. So if you go back to your reference sheet and check for cosine of alpha over 2, you would see that it's plus or minus, and a big square root, and then 1 plus cosine of alpha. And then what we need to decide is it the positive or is it the negative? And the way we decide that is coming back to this statement here, and it depends on where alpha over 2 is. So we want to figure out alpha over 2, and it looks like it's going to be sandwiched between 45 degrees and 90 degrees, which puts it in quadrant 1. Between 45 and 90 means it's a quadrant 1. Everything is positive in quadrant 1. So cosine of alpha over 2 would also be positive in quadrant 1. So we want the positive square root. So all that's left to do is simplify cosine of alpha. Remember, we figured that out right here. Cosine of alpha is negative 15/17. And then 1 minus 15/17 is 2/17. And then, excuse me, 2/17 divided by 2. Dividing by 2 is the same thing as multiplying by 1/2. So if we took 2/17 divided it by 2 or multiplied it by 1/2, we'd have 2 over 34. Or if we simplified that, it would be 1 over 17. And if we separated this now, if you have a square root like we have here of a fraction, then we can separate into 2 square roots, one of the numerator and one of the denominator. So it's 1 over the square root of 17, or square root of 17 over 17. The question 2, excuse me, is also standard 1, evaluating trigonometric expressions. We have a trig expression here, we have an inverse. So these don't automatically cancel each other out. Cosine, inverse, and sine aren't inverse functions. So what we need to do is evaluate sine 330. So if we go to unit circle, 330, and sine is the y value, so it's negative 1/2. And now we need to evaluate inverse cosine of negative 1/2. So back to the unit circle, and recall where cosine is defined. Cosine and inverse cosine was defined between 0 and 180, and cosine would deal with x values, so we need to find an x value in this range right here that's negative 1/2, and we have an x value of negative 1/2 right there, and that happens at 120 degrees. So going back, the answer to this would be 120 degrees. Okay, now cosecant, we would first determine the period and the period is 2 pi divided by b, and in this case, b equals 1/2. So it's 2 pi divided by 1/2. Dividing by 1/2 is the same as multiplying by 2, so the period is 4 pi. Now, there's no phase shift or there's no vertical movement moving the graph up or down. So I'm going to start at 0 here and go out distance of 4 pi. So there's one cycle, there's the length of one period. And then, again, since this is a problem where there is no phase shift, you do have to include and label the midpoint here, and then the quarter point, or the midpoint of the midpoint, which is 1 pi, and that one as well. Now, cosecant and secant don't have an amplitude. However, the way that we graph these, if you recall, is to graph sine or cosine first, and those do have an amplitude, so be right there, 3. And cosecant is the inverse, or rather reciprocal, of sine. So I'm going to graph first a sine function, which starts the middle of its amplitude. It's going to come up to 3, back down to the midline, and down to -3, and then up to the midline. And since this isn't a sine function, I'm not going to graph that with a solid line. I'm just going to use a dotted line. And then anywhere this graph crosses the x-axis is where cosecant is going to have a vertical asymptote. And it has one going through the y-axis. So this would be, in this, between those two vertical asymptotes, that's the minimum value, and it turns up like this. And then between these two asymptotes, this is a maximum value. It turns like that. The only difference in this problem, if it had been secant and not cosecant, is we would have started with a cosine function, which, if you remember, starts at the top of its amplitude here, and would have come down like that. So just know that this problem here involved cosecant, but you are going to also need to be familiar with secant. Be familiar with all 6 trigonometric function graphs: cosecant, secant, tangent, cotangent, cosine, and sine. That was our second standard. If you're keeping track on that, reflection sheet. Standard 2 is graphing a trig function. Question 4, also from standard 2. This one is graphing the tangent function. Biggest difference on tangent and cotangent is the period is pi divided by b. In this case, b equals 2, so it's pi halves. And if there are no phase shifts or vertical translations moving the graph up or down, then it's going to be centered around the origin here. And tangent has vertical asymptotes on either side of the y-axis, and the horizontal distance between those two vertical asymptotes needs to be pi halves. That's the length of one of its periods. So if I choose an arbitrary distance there, make those my vertical asymptotes, then this entire distance from here to here needs to be pi halves, because that's the period. So if I make this one negative pi fourths, and this one positive pi fourths, then from here to here is pi fourths, and from here to here is pi fourths, and if you add pi fourths plus pi fourths, you get pi halves. And then tangent function let's do like that for one of its cycles. For question 5, also from standard 2, graphing a trigonometric function, difference now is we have a phase shift, so this graph is actually going to move to the left. So 3 things we need to determine before graphing is amplitude. In this case it's 2, that comes from this value there. Period, that's going to be 2 pi divided by b. B is the value in front of x right here, and it's 1/2. And then the phase shift is the opposite of c divided by b, where this is c right here. So the opposite of that is going to be negative pi, excuse me, divided by 1/2, which is negative 2 pi. And it's also common, it doesn't happen to be the case in this problem, but it's also common for there to be a value here, like a +2 or something like that, which would move the graph vertically, so up and down. So just make sure that you look at some problems where we've done that. This one only has, however, shifting left and right, left in this case. So, come over here, for example. I'm going to make this my new 0, 0 right here. So this is negative 2 pi. And then the period is 4 pi, so the distance from here to the end of its cycle needs to be 4 pi. So if I start at negative 2 pi and then end at 2 pi, then that's going to give me a horizontal distance of 4 pi. And then period, the amplitude is 2. So using that same scale on my new x-axis up here. Now we're graphing cosine. Cosine doesn't start at the midline like sine does. Cosine starts at the top of its amplitude. One thing I forgot to do is if this is the end of the period, then you have to identify the middle and then the quarter points. I don't know why it keeps doing that. Okay, so cosine starts at the top of its amplitude, comes down to the midline, it's at the bottom of its amplitude, back at the midline, and then starts there at the top, or ends there at the top. So there's one complete cycle. Starting here and ending here, that would be the cycle there. All right, question 6 down. This is from that third major topic or major standard of trigonometry, which is solving trigonometric equations. So what I'm going to do here is get this equal to 0. So if I subtract 2 cosine then if I consider both of those terms, each of them have a cosine x as a common factor. So you factor that out, and you're left with the product of these two factors, both of which the product there equals 0, which means each factor must equal 0. So cosine x equals 0, and 2 square roots of 3 sine x minus 3 is equal to 0. Now solve each one of those equations separately. Here, if cosine x is equal to 0, that means that x is equal to the inverse cosine of 0. And we're restricted, it says here, we're restricted to 1 revolution of a circle, so from 0 to 2 pi. So looking at our unit circle, we need to find x values around the unit circle, x values around the unit circle that are 0. So we have an x value there and an x value here, both of which are 0, and that happens at pi halves and 3 pi halves. So for this one, we would say x equals pi halves and x equals 3 pi halves. Now for this other one, if we added 3 and then divided by, let's try that again, 2 square roots of 3 sine x, there we go, and then divided by 2 square roots of 3, then we would have sine x equals 3 over 2 square roots of 3, and I'm going to try to get rid of this square root of 3 in the denominator, so multiply it by square root of 3 over square root of 3, which is going to give me 3 square roots of 3 in the numerator, and then 2 times 3 in the denominator. The 3's are going to cancel, so that gives me square root of 3 over 2. So sine x equals square root of 3 over 2, which means x equals inverse sine of square root of 3 over 2. So sine deals with y values, so going back to unit circle, we need y values along the unit circle that are square root of 3 over 2. Y values that are square root of 3 over 2. So I see one here, and I see one here. The rest of the y values will be negative, so that happens at pi thirds and 2 pi thirds. So then we have 4 solutions there. X equals pi halves, 3 pi halves, pi thirds, and 2 pi thirds. Now for question 7, I'm going to try to get this expression there, or that sine squared 2x by itself. So I got to subtract 4. And then divide by 4. Now, if you square root both sides like that, you're going to get sine 2x equals plus or minus square root of 1/4. And then it's just something to keep in mind, 1/4 is square root of 1 over the square root of 4, which is 2. So this is just 1/2. So this is plus or minus, so sine 2x equals plus or minus 1/2. Now, we do inverse sine. I'm going to do this over here now. If sine 2x is equal to plus or minus 1/2, I'm going to separate this into two separate equations. Sine 2x equals positive 1/2, and sine 2x equals negative 1/2. So for this top one, I'm going to use inverse sine on both sides. And then same with this one, I'm going to use inverse sine. What we need to find then are y values along the unit circle that are 1/2. And really, while we're at there, we could look at for y values that are negative 1/2. Y values that are 1/2 or negative 1/2. So here's a y value of 1/2, 1/2. Here's a y value of negative 1/2. And here's a y value of negative 1/2. So it looks like pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. So 2x. Look, and remember there were two values of y where this was true. So 2x was pi over 6, and since on this problem we're not restricted from 0 to 2 pi, this just says solve the equation for x. We're not just going to have one revolution of a circle. We can have an infinite number of revolutions, and if remember, 2 pi is a revolution of a circle, and then k allows us to just keep going around the circle an infinite number of times. So pi over 6 plus 2 pi k, or 2x could equal 5 pi over 6 plus 2 pi k. Now down here for this one, the two values where this was true, where we had y values of negative 1/2, were at 7 pi over 6 and 11 pi over 6. So, didn't leave myself very much room here. So in this one, if I divided everything by 2, divided everything there by 2, then what I would get is x equals pi 12ths, and then again you divide that by 2, plus pi k. This one is x equals 5 pi 12ths plus pi k. This one is x equals 7 pi 12ths plus pi k. And finally, x equals 11 pi 12ths plus pi k. right, question 8, 9, and eventually on the next page, question 10. These are standard 4, which was a pretty substantial topic in trigonometry, finding missing parts of triangles. And we started in chapter 2, if you recall, just finding missing parts of right triangles, but then getting into chapter, I think it was chapter 4, we started getting into the law of sines, law of cosines, where we found missing sides or missing angle measures of oblique triangles or triangles that are not right triangles. So if I drew, let's try to make that a little better. And I call this angle C with 97 degrees. Then I'm going to call this angle B, so then side B over here would be 9 feet. And if I call this angle A, then side A here would be 29 feet. So what I have here is a case of side angle side, and that's law of cosines. And I'm finding angle A, so I want the version, if you remember there are 3 versions or variations of the law of cosines, and I want the version that involves angle A there, so I'm going to use that version of law of cosines. So now quick inventory of what we know. So I know side A, and I know side B, I don't know angle A. And I don't know side C. And this is problematic. You can't solve an equation if you have 2 unknown quantities here. So what we're going to have to do, even though this problem isn't specifically asking for this, we need to first find side C. So that's going to actually involve a different version of law of cosines. So lucky for us, we can get to do law of cosines twice in this problem. It looks like first to find side C, but we only need to find side C so that we can use it here so we can find angle A. So, yay. All right. C squared equals A squared plus B squared minus 2 times A times B times the cosine of C. So in a calculator, if we were to put this whole mess into a calculator, we have 9 squared plus 29 squared minus 2 times 9 times 29 times the cosine of 97 degrees. Make sure you're in degree mode, not radian mode. And let's see what we get here. So 9 squared. My calculator's telling me that I'm getting c squared equals 985.6. So then c would be the square root of that. So the square root, 985, is 31.4. All right, we no longer have c as an unknown value. Then we can solve this. 29 squared equals b squared. So that's 9 plus c squared minus 2 times b times c. It's cosine of a. So I'm going to subtract these two values here. So 29 squared minus 9 squared minus 31.4 squared. Then I'm going to divide by that quantity there. So divide by negative 2 times 9 times 31.4, and that is equal to the cosine of a. Now, that is a whole big mess to put into a calculator. 29 squared minus 9 squared minus 31.4 squared. It's negative 225.96, and then negative 2 times 9 times 31.4 is negative 556, or got that backwards, negative 565.2. That turns out to be 0.399. So a is the inverse cosine. Which is about 66.4. Okay. If we make, for question 9, if we make this our 102 degree angle, this could be angle B, 59 degree angle. And side A is 24. We need to find side B down here. So what we have here is an angle side, which is law of sines. And we're looking for side B, so I'm going to say B over sine B is equal to A over sine A. Those are the two parts of the law of sines I think will be useful to us here. So we don't know side B or little b, but we do know that sine B is sine of 59, and we know side A is 24 yards, and sine of angle A, sine of 102 degrees. So now, to solve this equation, we're going to multiply by sine 59 on both sides. So then B equals 24 times the sine of 59 over, or divided by, the sine of 102. Boy, that one was a little more straightforward. We like those ones. My calculator's telling me that side B is 21.03. And this would be in yards. Okay. We have some tree here. And this guy John wants to measure the height of the tree. So he walks 100 feet away. So here's a little guy over here. And the angle from the ground to the top of the tree, he measures to be 33 degrees. So how tall is the tree here? Well, this is the opposite. Because this is a right triangle here, this is the opposite, and this is the adjacent lengths. That's just tangent. So it's a pretty straightforward tangent problem. We could say the tangent of 33 degrees is equal to the opposite length over adjacent. Multiply both sides by 100. So we get x equals 100 times the tangent 33. Which is 64.94 feet. Quite a large tree there. Now, question 11 from our study of vectors, which was the last part of chapter 4, 4.3, I believe. So there's two of them, vector v and vector w. Part A is wanting us to sketch a diagram of the two vectors. And in this notation, we're saying that the initial point of the vector is on the origin, and these are the coordinates of the terminal. So 1, 5. So let's try that again. So there's vector v. And then 2, -3. Oh, I did miss that one too. Let's try that again. There we go. There's vector w. Okay. Now we need the magnitude and direction angle of each vector. So for part B, I need the magnitude of vector v and eventually the magnitude of vector w. So magnitude, it's the length of the vector. It's really just Pythagorean theorem. And then for vector w, so let's see, we got 4 plus 9, so that's square root of 13. And then the direction angle is the inverse tangent of y over x. So the inverse tangent of 5 is 78.7. And then remember, this formula gives you only angles in the first quadrant. So if the terminal point of that vector isn't in the first quadrant, then this becomes a reference angle. But for vector v, it is in the first quadrant. So the angle here is correct. It's 78.7 degrees. Now, for this other one, it's the inverse tangent of y over x again. So inverse tangent negative 3 halves is negative 56.31. And again, this would be correct if the vector is in the fourth quadrant, so we just got to check, and vector w is in the fourth quadrant. Otherwise, this would have been a reference angle. Now, question C is, what's the angle between the two vectors? Now, by going through part B, we could actually answer that if we know the angle from here to here is 78 degrees, and we know the angle from here to here is negative 56 degrees. We can just add those to, well, positive 56, but if we added those together, we get 135 degrees. The intent here, if we didn't go through the process of finding the direction angle of each vector, if it was just purely find the angle between two vectors, the intent there is to use, I think it's on the reference sheet here. Yeah. This formula here, finding the angle between two vectors. So what we need is the dot product. So that is what this top part of this formula is the dot product. And then those are the magnitudes there. So just for the sake of being thorough, let's go through this process, assuming we hadn't already found the direction angle of each vector. Oh, where'd you go? Here we go. So if I want the complete angle between here, let's call this, let's call that alpha, the angle between the two. So according to that formula, the cosine of alpha is equal to the dot product divided by the product of the two magnitudes. Now the dot product is a linear combination. It's the product of the x coordinates, or the x components rather, added to the product of the y components. So this would be 1 times 2, that's the product of the two x components, and we add that to the product of the two y components. So that's 2 plus negative 15, that's negative 13. And then the product of the two magnitudes, we've already found those. Square root of 26 multiplied by square root of 13. So if we type this all into a calculator, let's see, square root of 26 multiplied by square root of 13. We would have cosine alpha equals negative 0.707. we did the inverse cosine of that, gives us 135 degrees. All right, question 12, finding the horizontal and vertical components. So what we need is, let's say, for example, that this were vector v. We would need to be able to state vector v in terms of an x and a y, or a horizontal and vertical component, or we could write it in I plus j form. We would need the vertical and horizontal components. So the horizontal component is here, the vertical component is here. So really all this is here is a right triangle, and we need to know some components there. And we have the direction angle is 170, which means that this is a 10-degree angle. And we have the hypotenuse. So y and x. We can find y by using the sine, because this is the opposite side of a right triangle, and we have the hypotenuse. So y is equal to 50 times the sine 10, and x, since this is the adjacent length here, x would be a cosine value, so 50 times the cosine of 10. Again, make sure you're in degree mode on your calculator. 50 cosine 10 for the x value, that'd be 49.24. And then for the y value, 50 times the sine of 10 is 8.68. But if we look at where this vector is, it's in quadrant 2, and in quadrant 2, cosine needs to be negative, so that's something to keep in mind with this value. It actually needs to be negative 49.24. So we could say vector v is negative 49.24i plus 8.68j. Or we could use the other notation, negative 49.24, like that. All right, question 13, complex numbers we studied in chapter 5, and really very, very similar to vectors. So if we think about where this complex number would be located on the complex plane, where we have the real axis here and the complex, the vertical one is so 2 and the negative 3i, so the actual complex number is here. If you think about this in terms of a vector, we need to find out the distance there and the angle. So this is just Pythagorean Theorem. If we have 2 and 3, then r is equal to square root of a squared plus b squared. So 4 plus 9, that's 13. And the angle there is going to be the inverse tangent, -3/2, and I feel like we just did that one somewhere. I think it was question 11. Yeah, it's -56.31. And if you didn't want to have a negative angle there, it's fine to have it negative, but if you added 360 to that, then let's see, there we go, -56.1 plus 360, there we go. So that would be 303.7. Let's do 6.9. There we go. So the way that works in trigonometric form is 2 minus 3i is r cosine theta plus I r sine theta. And r was square root of 13, so this is going to be square root of 13. And then instead of doing cosine plus I sine, the abbreviation there was CIS. And then you put the angle. So this would be the answer to part A. This is that complex number in trigonometric form. Now for part B, using De Moivre's theorem, we need to evaluate z to the fourth. That's what De Moivre's theorem would tell us. That's on one of our reference sheets there. So r to the fourth would be the square root of 13 to the fourth power. And then 4 times the angle so the square root of 13 to the fourth power is 169. And then 4 times our angle is 1,214. .76. Now, that's a couple of revolutions. 1,214.76 degrees is a couple of times around the unit circle. So, twice around is 720. 3 times around a circle is 1080. So let's see what happens if I subtract 3 revolutions. So 1,214 minus 3 full revolutions of a circle, or 1,080 degrees, is 134.76. So just for the sake of what this looks like, I don't like an angle measure of 1,214 degrees. So I'm going to change this into 134. And that's just a coterminal angle, so 1,214 and 134. So the same angle, just 3 times less of a circle. Now this is trig form though for part B, and it does say specifically write your answer in standard form. So what we need to do then is convert 169 cosine of 134 plus 169i sine of 134.76. So we need to now figure out 169 times the cosine of 134, and that's negative 118.999, so let's call that negative 119. And then 169 times the sine of 134.76 is 120. Actually, it's more typical to put the I at the end, so 120 I. And that's our de Moivre's theorem there. So now 14 and 15, these were from chapter 6, conic sections. That equation there is in standard form already. This one is the general form. So you need to be familiar and comfortable graphing, first of all, determining what conic section we're dealing with in both standard or general form, and also graphing. It's a little easier when it's already in standard form. This, because of the plus sign there, and we have both variables being squared, y and x are being squared. This is an ellipse. We're going to have to complete the square here on 15 to figure out what the standard form is so we can graph that. Now, we have some translations here, so this is moving to the right 2 units and up 4 units. So to the right 2, up 4. Now, there's not going to have enough room here. Okay, let's try that. So what I've recommended always is that's going to become your new center point, or the new origin for our graph, to the right 2 and up 4. And then for ellipses, the largest value is A. And since it's here with the y variable, that value is going to go on the y-axis. So up 4 units in each direction. So here's 4. So those are the endpoints of the major axis. And then 3 units. Since this is associated with, that's not 9, that's got to be 3. There we go. B is the square root of 9, which is 3. Those are the endpoints of the minor axis there. So there's our ellipse. So this is the point 2, 0. This up here is the point 2, 8. This is the point 5, 4, and negative 1, 4. Now the only thing we don't have are the foci. So a squared minus b squared is 16 minus 9. So square root of 7. It's going to be 2 point something here. So it's 2.65. And the foci, rather that's plus or minus. There we go. The foci need to be on the major axis, which is the vertical axis here. This is the major axis. So 2.65 units from the center. So that puts right here. And right about there. Now we need the location of those. So this one is 2, and then we went up 4 to get to this middle point, and then we went up another 2.65. So that's 6.65. Now, this point here, we went up 4, but then down 2.65. So if you subtracted 4 minus 2.65, would get 1.35. So 2 and then 1.35 for the two foci. And that's what it means by label all important characteristics. We have the endpoints of the major axis, the endpoints of the minor axis, and then the foci. And that's in the case of an ellipse. If this had been a parabola, we would need the focus, the directrix, and the vertex, and 2 other points on the parabola. If this had been a hyperbola, we would need the vertices, the foci, and you'd have to draw in the slanted asymptotes. Question 15, we first need to complete the square. To write the equation from general form into standard form. So I'm going to get the x variables together and factor out a 9. So I'm going to have just x squared plus 2x. And then to complete the square here, I'm going to need half of 2, which is a 1, and then square it. So I'm going to have a plus 1. And if I add the 151 on this side, since I added a 9 right here, I'm going to have to add a 9 over on the other side. Now for the y variable, I'm going to factor out, that's actually a minus, factor out a 16, and that leaves me y squared plus 2y. Because if I factor out a negative 16 from negative 32, I get a positive 2. And then to complete the square there, I'm going to get half of 2, which is 1, and then square it, which is 1, but I really subtracted a 16 on this side, so I'm going to subtract a 16 there. And then this factors into that. And this factors into that. Then 151 minus 7. Let's see, 151 plus 9 minus 16 is 144. So divide everything now by 144. So this is a hyperbola. Because of that minus sign there. We could have also used the conic identification theorem, which you have on one of your formula sheets, to figure out it was a hyperbola. Still, you would have to have completed the square to get this into standard form so you could graph it. And we've got a horizontal translation to the left one, and then down one. And then on hyperbola, it doesn't matter which is the larger value, it's just whichever one is listed first, whichever one is part of the positive fraction, that's a, not necessarily because it's larger, because it's listed first. So a equals 4, b equals 3. And since this value is with the x variable, then 4 units in the x direction. And then since this value here is with the y variable, that's 3 units in the y direction. So all of these values are going to help us draw that central box. That's the width and the height. Central box, and then we can use that central box slanted asymptotes. And since the x variable is part of that positive fraction, that's what makes this a horizontal hyperbola. So we have a piece there and a piece there. So these are vertices. Those need to be labeled, those points, or the location of those points. So this one is -5, -1. This one here is 3, -1. Now we need the two foci. And this is a squared plus b squared. So 16 plus 9 is 25. So c equals plus or minus 5. So that's 1 unit further away than the vertices. So the location of focus 1 would be -6, -1, and the location of second focus would be 4, -1. Let's clean this up here. There we go. So this is the equation. There it is in standard form. And then there's your graph. Okay. Question 16 to 17. Polar coordinates. This is also from chapter 6. Very last thing we talked about in the course. We're converting from rectangular. So these would be your traditional, you go right, square root of 3, and then down, -1 units. That's rectangular coordinates, where in polar coordinates, we need to know a distance and then an angle that it turns. So right now, this is an x and a y value. What we need to convert this into is r and theta. So the conversion factors is r equals square root of x squared plus y squared. So the square root of 3 squared is 3. 3 plus 1 is 4. Square root of 4 is 2. So r equals 2. Theta, much like finding the direction angle of a vector, it's the inverse tangent of y over x. So if we did the inverse tangent of -1 divided by the square root of 3, it's -30, or 330. 333. 300. Again, you just got to think that's in the fourth quadrant, and this point would be in the fourth quadrant, so that's the angle we want. It's not a reference angle, that's the angle we want. So this would be 2, 330 degrees. That's the corresponding location of that point on the polar plane. Now we need to graph that. So point A would be second circle out, which is here, and then 330 degrees, which is right here, second circle. Actually, that's 300, this would be 330, right there. All right, now we know B is going to be right on the x-axis, -2, 0. Right there, but we need the location of that in polar coordinates. So just looking at this, we know the distance from here to here is 2, and then the angle is 180 degrees. But if we wanted to go through the whole process, we would have and then theta would be the inverse tangent of y over x, and that is, the inverse tangent is 0. Now your calculator is going to tell you that this is 0. But you need to remember that sometimes when you do this process, it gives you reference angles or angles that aren't quite where you need them. And we know this is going to be over here, because -2, 0 is right there, and that angle is 180 degrees, so this was a reference angle. So theta is going to be 180 degrees. So 2, 180 is right there, point B. Now for part C, same process. Just x squared plus y squared. So 3 root 3, I'm talking about right here. 3 times the square root of 3 squared, that's going to be 9 times 3, which is 27 fourths. So this is 36 over 4, which is the square root of 9, which is 3. And then theta, inverse tangent of 3 root 3 over 2 divided by -3/2. So if we wanted to do some arithmetic over here, 3 root 3 divided by 3/2 is the same as multiplying by 2/3, so the 2's and the 3's cancel, so essentially just left with -√3. if we do that on a calculator, it's negative 60. But considering where this is, negative 3/2, comma 3/2, that's in quadrant 2. So calculator tells us negative 60, but that's just a reference angle for 120 degrees in the second quadrant. So we're going to use 120 degrees for theta. So then the angle, or sorry, not the angle, the point would be 3 comma 120. And that would be right there. Okay. Now we're going the other way. We have polar coordinates, and we need to convert those into x, y, rectangular coordinates. So the conversion factors there, if we had a point that's 4, then pi thirds is 60 degrees. So let's say that this was the fourth circle, and pi thirds would be right here. So we need the so we know that the distance there is 4, and that the angle is 60 degrees. So we need the y and x coordinate. So this is like finding the vertical and horizontal components of that vector that we did a few problems ago. So let me see if I can. So it's the fourth circle out, so it's a distance of 4, and we have an angle measure of 60 degrees. So it's it's really the same process we did with that, there's problem 11 or 12, one of those where we had to find the horizontal and vertical components of the vector. Really no different. X was equal to r cosine theta, y is equal to r sine theta, r is 4, so it's just 4 cosine pi thirds. This is 4 sine of pi thirds, so calculator time. 4 cosine pi thirds is 2, and 4 times the sine of pi thirds is 3.46. So it'd be the same exact process here for part B. So 3 times cosine, negative 150, is negative 2.6. And 3 times the sine of negative 150 is negative 1.5. And I think that is it.